So from the previous video, we defined the conductivity as a collection of properties of the metal and the electrons. We've got the electron charge, number of electron density, and the drift time and the mass. And we find that our current can be defined as the conductivity, the area, and the electric field. So our conductivity, sigma, is a single measurement, we don't have to worry about any of this, of how good the metal conducts electricity. We can look it up for any given metal, we can find the number for it, and this is really, really nice. What might be often as useful is how badly it conducts electricity. So we're going to define that, rho, as 1 over sigma. So we're going to call this rho our resistivity. So if we do that, then we can rewrite our current as AE over rho. And that's a good step. Another good step is our electric field is something we feel hopefully pretty confident about, pretty good about, but there's something similar to electric field that we feel as confident or more confident about, and that's delta V. Delta V is, right, negative E dot delta S, or we can say that our E is the negative of delta V delta S. We can do a full derivative if we want, but we don't really need to. So every time we see our electric field, we can change it to our delta V over delta S, two measurements that are a lot easier to make than the electric field itself. So now we have that our current is A with a negative delta V over rho delta S. So now that we have this A is the area of our wire, and this delta S is the length of the segment of the wire. So we can choose, right, the entire wire or just a fraction of it. And this delta V is the potential difference between the ends of our segment. So this is looking really, really good, right? And we can do one more simplification to really help ourselves out. If we look at this A, if we look at this delta S, and if we look at this rho, right, once a wire rolls off the factory, it's going to be made of the same metal, and it's going to still be made of the same metal, so its resistivity doesn't change. It's always going to have the same area, assuming, right, we don't do any super destructive things to it, and any given segment, and usually we just do the entire segment of the wire, will have the same length. So in fact, just as we compressed all of this conductivity measurements into conductivity, we can compress all of these into one measurement. So we can define R as our resistance. And so R is going to be rho delta S over the area. And so this is how badly it conducts, similar to the resistivity, but now with the full things of the wire as well included. And now when we get this, we can take a look at our, right, full current is going to be negative delta V over R. We can rearrange and solve. One of the more popular ways to solve it, there's only really three, is saying delta V is equal to negative IR. Usually when we do this, we don't really worry about sign conventions, and similarly for our R, we just say it's, right, the magnitude of delta V over I. We're not worrying too much about direction for these kinds of things. So this right here, these are Ohm's laws. But let's remember how we got here, right? We assumed back here that we had a metal. If we don't have a metal, we might not or shouldn't be able to use Ohm's laws. We assumed that the charge carrier was an electron. If our charge carrier is an electron, we can't use Ohm's law. And we made a couple other assumptions about drift velocity. These turn out to work really, really well for metals. In fact, most of the things we work out will do that. But there are non-ohmic devices like diodes, like transistors, like ion seawater and stuff like that, that will not follow Ohm's law. But this is Ohm's law, and this is how we get to use it. So very often we'll then say, just for an R, That right. This only works for a resistor, which is something that